Today we're going to be looking at Einstein's theory of special relativity and trying to derive the equation for time dilation. So before I start, I want to provide a little bit of context just so you can understand what's going on. So my favorite way to think about this is to imagine you're on a train, and let's say the train here has a torch at the bottom and it fires it up, and let's imagine there's a detector here or something. All right, so what we're going to do is define that distance there, and we know that distance is speed times time, so I'm going to call that c as the speed of light times t naught. So I'll tell you why I'm using t naught later on. So on the other hand, let's imagine that someone on the platform is watching the train. All right, very tall man here. Anyway, so what happens in the eye of the person in the platform is that the train is moving at a distance of v. So we're going to define this distance that the train moves as vt. And what happens is the light also moves, but unlike for the person in the train carriage, it doesn't move straight up. It would move diagonally because the train is also moving. So I'm going to draw this diagram out better here. So we define the distance here as c times t naught. So what I'm going to call this bit is vt, and because traveling at a speed v, and again we have light here, so it's ct this time. So you might be wondering, why am I using t on these two sides of the triangle but t naught on this side? So according to special relativity, the speed of light is always constant in free space. So that means time and distance can be relative. So for the person inside the train, all they can see is a light going up, and for them it's the distance of speed times t naught. On the other hand, only the person outside the carriage can observe the train moving. If you're inside the carriage, you won't be able to observe the train moving, and also only the person outside the carriage can observe the light going in a diagonal path. So now we understand that, we just really need to do some Pythagoras. So we have vt all squared plus ct naught all squared is equal to ct all squared. So if we just expand this out, so we get v squared t squared plus c squared t naught squared is equal to c squared t squared. So what I'm going to do is bring this term with the other t squared in to the right side. What we can do now is factorize the t squared, and then we'll end up with this. Because we're deriving time dilation t, we're trying to get that on its own. So what we're going to do is divide by the bracket. So we'll have c squared t naught squared over c squared minus v squared. Now for the next step, it's sort of like a magic step, because what we're going to do is try and cancel out the c squared. So what we're going to do is leave the top as it is. So we're going to have c squared t naught squared over, and then we'll take out a factor of c squared. So on the left side we'll just have 1, and on the right side we'll have v squared over c squared, because then if you multiply by the c squared you only get v squared. So we can cancel out the c squareds, so we get t squared is equal to t naught squared over 1 minus v squared over c squared. And finally we're going to square root it, so we're going to get t is equal to t naught over the square root of 1 minus v squared over c squared. Now you may sometimes see it written like t naught times 1 over square root of 1 minus v squared over c squared, and that's because this term here is also called the Lorentz factor, or you may see it written as gamma.